Hey everyone, and welcome back to the channel. Have you ever looked up at the night sky and wondered about the sheer, unimaginable power radiating from every single star? What if I told you there's a concept, once thought to be pure science fiction, that proposes we could actually harness the energy of an entire star? Get ready, because today we're diving deep into the awe-inspiring, universe-altering idea of the Dyson Sphere. Imagine a structure so vast, so technologically advanced, that it could completely encase a star, capturing nearly every photon of energy it emits. This isn't just a wild dream from a sci-fi novel. It's the core concept behind the Dyson Sphere. It's a theoretical megastructure designed to solve humanity's energy crisis on an astronomical scale. This incredible idea was first popularized by the brilliant physicist Freeman Dyson in 1960. He wasn't thinking about a solid shell, but rather a sphere of orbiting collectors. His vision was a testament to humanity's potential for engineering on a cosmic level, pushing the boundaries of what we consider possible. At its heart, the Dyson Sphere is about energy collection, but on a scale that dwarfs anything we currently conceive. Think about it. Our own sun, a fairly average star, blasts out an astonishing 388 quintillion watts of energy every single second. That's more power than all of human civilization has ever used combined in its entire history. Just imagine for a moment what humanity could achieve if we could tap into even a fraction of that boundless energy. We're talking about powering entire civilizations, not just on one planet, but across multiple worlds. It could fundamentally change our relationship with resources and technology forever. This isn't just about having more electricity for our homes. It's about unlocking capabilities that are currently beyond our wildest dreams. From interstellar travel to terraforming planets, the energy potential is truly limitless. One of the most compelling and, dare we say, achievable designs for a Dyson Sphere is known as the Dyson Swarm. This concept moves away from the idea of a single, solid shell, which presents immense engineering challenges. Instead, it envisions a vast collection of independent objects. Picture thousands, even millions of individual solar collectors, power satellites, and habitats, all orbiting a star in a dense, organized formation. Each of these units would be designed to capture stellar energy. They would then convert it into usable forms, like electricity or microwave radiation. This collected energy could then be beamed back to a central receiving station, perhaps a planet, a moon, or even a massive space habitat. The beauty of the Dyson Swarm lies in its modularity and scalability. We wouldn't need to build the entire structure all at once. Instead, we could start small, deploying a few collectors and gradually expand the swarm over centuries or even millennia. This phased approach makes the Dyson Swarm seem far more attainable than a solid shell. It aligns with our current technological trajectory. We already have experience launching satellites and building space stations. The challenge isn't necessarily the fundamental technology, but rather the sheer scale and coordination required. We'd need advanced robotics, AI, and self-replicating systems to manage such a colossal undertaking. These individual collectors could be specialized. Some might focus purely on energy conversion, while others could be habitats for the construction crews or even entire populations. This distributed nature also offers resilience. If one unit fails, the entire system doesn't collapse. The Dyson Swarm represents a truly monumental engineering project, but one that builds upon technologies we are already developing. It's a testament to human ingenuity and our relentless drive to push the boundaries of what's possible in space. Now, let's consider the most iconic and perhaps most challenging version of this megastructure, the Dyson Shell. This is the truly ambitious design that involves building a single, solid, continuous structure completely enclosing a star. It's the image that often comes to mind when people hear Dyson Sphere. While incredibly intriguing from a theoretical standpoint, the Dyson shell presents a myriad of engineering and material science challenges that are almost unfathomable with our current understanding. The scale alone is mind-boggling. First, consider the materials. What kind of material could possibly withstand the extreme temperatures and intense radiation levels just a few million miles from a star's surface? We're talking about temperatures that would vaporize almost any known substance. Then there's the structural integrity. A shell of this size would be under immense gravitational stress from the star. It would need to be incredibly strong, yet also incredibly light, to avoid collapsing under its own weight. The sheer mass required would be astronomical. Furthermore, How would such a structure maintain its position? It couldn't simply sit around the star. It would need active station keeping or some form of propulsion to counteract gravitational forces and maintain a stable orbit. This would require constant energy input. The logistics of construction are equally daunting. Where would we get enough raw materials to build a shell with a surface area billions of times that of Earth? We'd need to dismantle entire planets, or perhaps even multiple planetary systems, to gather the necessary resources. And what about the heat? A solid shell would absorb all the star's energy, but it would also need to radiate that heat away to prevent itself from melting. This would require an incredibly efficient heat dissipation system, likely radiating waste heat into space. The Dyson shell, while a captivating concept, pushes the very limits of physics and engineering. It represents a technological leap so profound that it might be considered the ultimate achievement for a Type II civilization on the Kardashev scale. So, how could humanity even begin to construct such a monumental project, whether it's a swarm or a solid shell? The answer lies in advanced robotics, artificial intelligence, and a completely new approach to resource acquisition. We're talking about engineering on a cosmic scale. First, we would need highly advanced, autonomous robotics. Imagine fleets of self-replicating machines, often called von Neumann probes, capable of mining asteroids, comets, and even entire planets for raw materials. These probes would be designed to extract, process, and assemble components without direct human intervention. These robotic systems would operate in the harsh vacuum of space, enduring extreme temperatures and radiation. They would be programmed with complex AI to manage construction, maintenance, and expansion, working tirelessly over centuries. The raw materials themselves would likely come from the asteroid belt, or perhaps even from gas giants like Jupiter, which contain vast amounts of hydrogen and helium. Mining operations would need to be incredibly efficient and on an unprecedented scale. These materials would then be transported to orbital construction yards, where automated factories would fabricate the individual components of the Dyson swarm or the massive panels for a Dyson shell. This would be a continuous, self-sustaining process. The construction timeline would span centuries, if not millennia. It wouldn't be a project completed by a single generation, but rather a multi-generational endeavor, a testament to the long-term vision and collective will of an advanced civilization. This might seem like a far-off dream, something out of a futuristic movie. However, advances in AI, robotics, and space exploration are happening at an incredible pace. The foundational technologies are slowly but surely being developed, bringing this grand vision closer to reality. The potential benefits of a Dyson Sphere extend far beyond simply solving our energy needs. This technological marvel could fundamentally transform human civilization and our place in the cosmos. It's about unlocking a new era of possibilities. With an essentially infinite energy supply, we could power entire civilizations on distant planets, making interstellar colonization not just possible, but sustainable. Imagine terraforming Mars or other barren worlds, creating new homes for humanity, all fueled by a captured star. This abundance of energy would also fuel unprecedented advancements in technology. We could develop faster-than-light travel, advanced computing systems capable of simulating entire universes, and medical breakthroughs that could extend human lifespans indefinitely. Resource scarcity, a major driver of conflict and inequality on Earth, could become a relic of the past. With access to vast amounts of energy, we could synthesize rare elements, recycle materials with incredible efficiency, and create a post-scarcity society. A Dyson Sphere could also serve as a massive protected habitat for billions, even trillions of people. It would be a self-contained ecosystem, shielded from cosmic radiation and the vacuum of space, offering a new frontier for human expansion and survival. Furthermore, the sheer scale of such a project would necessitate global cooperation and unity. It could be the ultimate unifying goal for humanity, transcending national borders and cultural differences, focusing our collective efforts on a shared, monumental achievement. It's about ensuring the long-term survival and flourishing of humanity, not just for a few centuries, but for billions of years. A Dyson Sphere represents humanity's ultimate insurance policy against cosmic catastrophes and the eventual death of our own sun. While the allure of a Dyson Sphere is undeniable, we must also consider the profound challenges and ethical dilemmas such a project would present. It's not just about engineering, it's about cosmic responsibility. One of the most significant concerns is the environmental impact on the solar system. If we were to partially or fully enclose our sun, it would drastically alter the amount of light and heat reaching the planets. This could lead to a stellar dimming effect. What happens to Earth, Mars, or other planets if their primary energy source is partially obscured? It could trigger catastrophic climate change, plunging worlds into an ice age or disrupting delicate ecosystems. Balancing our energy needs with cosmic responsibility will be essential. The sheer scale of resource extraction required would also be immense. Dismantling asteroids, moons, or even planets to gather materials raises ethical questions about planetary preservation and the sanctity of celestial bodies. Are we willing to sacrifice other worlds for our own expansion? And there's the question of control. Who would own and operate such a powerful structure? The potential for a single entity or nation to control the energy output of an entire star could lead to unprecedented power imbalances and conflicts. The construction itself would be a multi-generational project requiring immense societal commitment and resource allocation. Would future generations agree to continue such a monumental task? Or would priorities shift, leaving an unfinished megastructure? There are also unknown unknowns. What unforeseen gravitational effects could such a massive structure have on the solar system? Could it destabilize or create new, unpredictable phenomena? We are talking about altering fundamental cosmic processes. The ethical implications extend to the very definition of humanity. Would living inside a manufactured shell, completely detached from a natural planetary environment, change what it means to be human? These are profound questions we would need to grapple with. Beyond our own aspirations, the concept of a Dyson Sphere opens up one of the most exciting discussions in astrobiology: the search for extraterrestrial intelligence, SETI. If advanced civilizations exist elsewhere in the universe, it's plausible they might have already built such megastructures. A Dyson Sphere would be an unmistakable techno-signature, a technological signpost of intelligent life. It would dramatically alter the light signature of a star. Instead of seeing a bright, hot star, we might observe a star that appears unusually dim or emits an excess of infrared radiation. This infrared signature would be the waste heat radiated by the Dyson Sphere itself. Imagine a star that looks normal in visible light, but glows intensely in the infrared spectrum. That would be a strong indicator of an artificial structure surrounding it. Astronomers are actively looking for these kinds of anomalies. Projects like the Tabby star, KIC 8462852, have generated immense excitement, precisely because their unusual dimming patterns could, theoretically, be explained by an incomplete Dyson swarm. While natural explanations are more likely, the possibility remains tantalizing. Detecting a Dyson Sphere around another star would be the ultimate confirmation that we are not alone in the universe. It would provide irrefutable evidence of an advanced civilization, a Type II civilization on the Kardashev scale, capable of harnessing the power of its home star. Such a discovery would fundamentally change our understanding of life, technology, and the potential future of our own species. It would be a profound moment in human history, forcing us to reconsider our place in the cosmos and inspiring new avenues of scientific inquiry. The search for these cosmic megastructures is a testament to our curiosity and our desire to connect with other intelligent beings. It reminds us that the universe is vast and full of wonders, both natural and potentially artificial. In the end, the idea of capturing the energy of an entire star might seem like a distant fantasy, a concept relegated to the pages of science fiction. Yet, it represents something far more profound, an aspiration that pushes the very limits of human imagination and determination. The future may hold possibilities we can only dream of today, igniting our thirst for knowledge and exploration across the cosmos. Whether we ever build one or not, the concept of the Dyson Sphere inspires us to think bigger, to reach further, and to imagine a future where humanity thrives among the stars. If this deep dive into Dyson Spheres has sparked your imagination and left you hungry for more cosmic wonders, then you absolutely need to join our community. Hit that subscribe button right now and turn on notifications so you never miss another mind-bending exploration of science, technology, and the universe. What other megastructures or futuristic concepts would you like us to explore next? Let us know in the comments below. Your ideas fuel our next adventure.